5. Okay, so we've got 3 things to take notes on today. And the first one is from 5.2, which is on factoring. So let's go ahead and start out by reviewing the opposite of factoring, which is foiling. So let's quickly go through this together. If we FOIL this, what do we get when we multiply the first two? Yep. And the outside two? Bueller. What's that, Taylor? Ferris Bueller spells his name differently than I spell my last name. Ferris is with an E. Ferris Bueller. If you haven't seen Ferris Bueller Stay Off, it's the absolute classic standard skipping school movie from the 80s, so I highly recommend it.
Wait, for some reason you showed it in my school movie night.
Oh, really?
Yeah.
They try to give you guys some ideas.
I don't know why.
Yeah. Skip school, go steal your friend's dad's extremely expensive car.
I think that's because most people voted for it. But
Oh,
like,
wow.
But just like, I don't even know why they put it there in the first place.
Yeah, it's just like, why was that on the ballot? But secretly, all your teachers love that movie.
I think they do. My math teacher goes Bueller when no one answers. I think he likes that movie.
Yeah. No, it's a classic. That's why I'm just standing here. So I'm just saying, and what do we get when we multiply the outside two? Yes, thank you. Yes, plus 2x and minus 8. And what do we get when we combine these like terms? Yes. So y equals x squared minus 2x minus 8. Okay, so that's how foiling works. Basically, we're going from an equation in intercept form to an equation in standard form. And these specifically are quadratic equations, but this also works for cubic equations and quartic equations and so on and so forth. And you'll get more practice with that in pre-calculus. Okay? We're just focusing on quadratic equations right now. All right, but let's say that we don't start with intercept form. Let's say that we start with standard form and we're told to factor it. Let's say we're trying to figure out what the intercepts are. Is there going to come a moment in this class where you announce at its introduction that you love doing it, Taylor?
Yes.
Yes! Okay, good. Well, I shall look forward to that with great anticipation and delight. But in the meantime, we are going to factor this equation. Who wants to explain a method for how we basically reverse FOIL? How do we go from standard form to intercept form? Yes, Lily.
Well, we can start by just writing x and x in each one of the parentheses because there is no function for x, so we know that's just going to be x.
That's exactly right. So I already feel like I'm halfway done with the problem when I just write this, because we know that if we're factoring it that we're going to end up with the product of binomials, and we also know to start out with the only numbers, or the only things that multiply together to give us x squared is going to be x and x. This is our only choices when we're factoring, so that makes that part easy. Yes, Gio?
And then you wait.
What's that?
Wait, am I supposed to, am I supposed to be asking a question or can I?
You can ask a question or answer a question.
Then you find a number that multiplies to -8, that adds or subtracts -2.
That's right. So now we need the factors of -8
-4 and 2.
that combine to -2. So we're looking for two numbers that when we multiply them give us -8, and when we combine them give us -2. Yes, Cece?
What is this method called? I never ever remember what they call each factor method ever.
So this is just factoring.
That's it?
That's it.
But there's other ways to factor too though, right? So then they're all just
Different methodologies and like different like little.
Yeah, what do we call this one?
The Bueller way? I don't know.
No.
I don't know. I don't know what the official name of this technique
Yeah,
is.
I
I
don't- I
probably
never
should
heard it.
know. There are different ways of doing it, but this one I feel like is the most straightforward, especially for what we're doing now. And repeat for me then, Gio, what are the two numbers that when multiplied give -8 and when added give -2?
-4 and 2.
That's right. So if we multiply -4 and +2, why is this 2 so weird? We multiply -4 and +2, we get -8. And if we combine them, we get -2. And so now we have successfully factored this. Okay, sub question. Since this is now an intercept form, where would the graph of this parabola cross the x-axis? Gino. Where would this parabola cross the x-axis? Ah, okay, so here enters the, so Gino first said -4 and 2, and then restated and said, oh, wait a minute, 4 and -2. Why does it have to, because doesn't this look like -4? Doesn't this look like +2? Why does this have, why is it actually 4 and -2? Yes, Gio.
Because you're setting x minus 4 and x plus 2 equals 0, and so you have to add 4, and so x equals 4.
That's right. Because if we're on the x-axis, what's the y-intercept have to be? Or not the y-intercept, what does the y-coordinate have to be?
0.
It has to be 0. So in order for y to be 0, either this binomial must equal 0 or this binomial must equal 0. And 4 minus 4 is 0, and -2 plus 2 is 0. Okay? These are the x-intercepts, and these are also known as the solution. So it's important to note that these two words are synonymous in algebra. If you are asked to solve a polynomial, and again, this doesn't just apply to quadratics, this could be a cubic equation or a quartic equation, so on and so forth. But if you are asked to solve the equation, you're looking for the x-intercepts. If you find the x-intercepts, you have found the solutions. Those are totally synonymously interchangeable as far as polynomials are concerned. Okay, I also want to direct your attention to page 257 in your book. And you will see that there are examples on page 257 of some really important patterns, which are the difference of two squares and the perfect square. Trinomial. So difference of two squares and perfect squares. If you see those references in the chapter, this means that you have a shortcut, because these kinds of setups follow this very specific pattern. In particular, the difference of two squares is going to be also important in chapter 5.4. So let's take a look at the difference of two squares. Let's say that we have y equals x squared minus, does somebody have a favorite square number?
36.
So this is called the difference of two squares because we're subtracting one square from another square. And this is very easy to factor because it's just going to be x plus 6 times x minus 6. The reason that the x term, and we can see here why the x term sort of like disappears, it drops out of the picture. It's because when we FOIL this, we get x squared minus 6x plus 6x minus 36. And so the x terms disappear. So when we factor the difference of two squares, you know, we get x plus the square root times x minus the square root. And in this exact setup, when we FOIL it, the x term disappears. All right, and here with the perfect squares, it's also important to note, and we went over this yesterday, but if I have y equals x plus 2 squared, Merlin, is it going to be x squared plus 4?
No.
What is it going to be?
It's gonna be x plus 2 in parentheses times x plus 2.
That's right. And when we do that, we are going to end up with an x term. We're going to have x squared plus 2x plus 2x plus 4, or in this case, x squared plus 4x plus 4. These two numbers aren't always going to match. I should have picked a number other than 2. Here they match because 2 plus 2 is the same as 2 times 2. But you can see on page 257, in the green box at the top of the page, what those special patterns are. And so that will come up in the chapter 5.2 assignment. Does anybody have any follow-up questions on what is up on the board right now? Okay, so this can be a handy technique for solving a quadratic equation, because if you factor it, you've got it in intercept form, and if you know the x-intercepts, then you know the solutions, because they are one and the same. All right, then we are going to skip ahead to 5.4. Which is imaginary numbers. All right, and we're going to telegraph ahead a little bit. The reason why imaginary numbers come up in the chapter on quadratic equations is because we're going to need imaginary numbers in order to solve certain quadratic equations. Okay? This parabola has two real solutions because it crosses the x-axis in two real places. Is it possible to have a parabola with just one solution? What would that look like? Yeah. So if our little parabola is very cutely perched like a little parakeet right on the x-axis, on its vertex, then we have just one real solution. But how many real solutions does this parabola have? None. Because this doesn't cross, it doesn't really cross the x-axis anywhere. But that doesn't mean that its solutions are undefined. It just means that they are imaginary. So like the unicorn, if I say the word unicorn, you know, maybe you're picturing like one of those majestic 1980s style t-shirts with a big unicorn like splashing like through, like a graphic t-shirt with like a big like white unicorn splashing through the waves on the beach. I'm not saying I did or I didn't have a t-shirt like that in the 80s. I'm just painting a picture for you. Or maybe you are picturing Sunbeam, the My Little Pony turquoise, white mane, yellow stripe, gold glitter sun emblem on derriere. I'm not saying I did or I didn't have Sunbeam the My Little Pony in the 1980s. I don't know why there were so many unicorns in the 1980s, but there were. But there may be slight differences between the unicorn you're picturing and the unicorn I'm picturing, but in all likelihood, all of us are imagining an equine quadruped with a single horn protruding from the forehead. And that is the same with imaginary solutions. This is different from undefined. Slope that's undefined is sort of like Pandora's box. It is chaos. It could be anything. It is a total mystery. Imaginary numbers are not a mystery. Imaginary numbers are well defined. They're just not real. Sorry if you thought up until today the unicorns were real.
How dare
Don't-
you break so many people's hearts.
Oh, I'm sorry. Okay, so where then do imaginary numbers come from? So this is, let's say, we'll take your favorite perfect square, Merlin. If we square 6, we get 36. In other words, 6 times 6 is 36. If we square negative 6, in other words, we multiply negative 6 by negative 6, we also get positive 6. So then the question arises, what number can be multiplied by itself to give us negative 36? Exactly. There's not a real number. Because we have two options. We have 6 and negative 6, and neither of those produce negative 36 when multiplied. They both produce a positive 36. So this is why we have imaginary numbers. And all imaginary numbers include the square root of negative 1, which we label I. So we can clearly define the concept. We're taking the square root of a negative number. In other words, here we can take the square root of 36 and we can get 6, or we can take the square root of 36 and get negative 6. But just try and take the square root of negative 36 in your calculator. What does it say?
Yeah. I tried that earlier.
Yeah. Error.
Unreal.
Unreal.
Carol. And it says, in real mode, all calculations must result in a real number.
In real mode.
It's in real
Yes.
mode.
Yes,
So
imaginary
you probably
numbers.
have a complex mode on your calculator.
Whoa.
So that might be something to look at in the menu.
Wait, wait.
So the way that then we answer this question, and I want to make sure that this is definitely visible, because I feel like this is sort of drifting out of where everybody can see. But if we try to take the square root of negative 36, for example, we need to separate it into its real and imaginary components. So negative 36, in fact, I'm going to really explicitly show every single step here. This is the square root of 36 times negative 1. So negative 36 is 36 times negative 1. And if we have the root of a product, we can take the product of the roots. So we can rewrite this as the square root of 36 times the square root of negative 1. The square root of 36 is 6. Negative 1 is I. So the square root of negative 36 is 6i. Yeah, yes, thank you, thank you. Okay. A complex number looks like a binomial, and it has a real part, and it has an imaginary part. So for example, we could have let's go ahead and use our example before. We could have -4 plus I and we could have 2 plus I. So these are two, they kind of look like binomials, but instead of x's, we have i's. Typically in complex numbers, the real part comes first in the order, and then the imaginary part comes second in the order. And now we can add them, subtract them, multiply them, just like other binomials. So what I mean is, let's say that we're going to add these two together. We just combine the real parts, and then we combine the imaginary parts. So what's -4 plus 2? What's I plus I? 2I. Yep. Okay, so we just added two complex numbers to get a complex number. If we multiply them, we basically do foiling. So we're going to end up, this is a very similar to the factoring example that we did before. So we're going to get -8 minus 4I plus 2I plus I squared. So we've got -8 minus 2I plus I squared. Okay, but here's where we're going to have an extra step that we didn't have when we were foiling. Because I squared is the square root of -1 times the square root of -1. Well, we're not adding them though, we're multiplying them. Let's say that we multiply, let's take a different example. Let's say we multiply the square root of 36 times the square root of 36. What do we get?
36I.
Well, here there's no i's. This is just a numerical example. So we've got 6 times 6, which is 36.
Oh, yeah.
So we're squaring.
So it's.
We're squaring the roots. So here, when we do that here,
Yeah.
and we square the roots, what do we get?
And I times I is I squared.
It's I squared, but what's the square root of -1 times the square root of -1? What do we get when we square the square root?
-1.
Yeah.
Oh. Never mind.
Yes. So guys, this is one of my favorite things in all of math. Because that's like the wardrobe to Narnia or platform. You're going to have to help me.
9 3/4.
Yes, platform 9 3/4. I squared is the portal between the real and imaginary worlds.
So it means that we.
So
if
we
you
went-
get to 1, you can just say that it's I squared. Like, if you get the answer -1, you can just write it down as I squared.
And likewise, importantly here, for simplifying our product expression here, where we see -8 minus 2i plus I squared, this is -8 minus 2i minus 1. And now we have like terms again that we can combine. We have constants, and so we've got -9 minus 2i. And this will be our final answer if we're told to find the product between these two complex numbers. because I squared is negative 1, and vice versa. Okay, when you get to the place when you're dividing complex numbers, let me know. And we'll go over how to do that. Is anybody still writing down what I have up here on the board?
Yep.
Yep, okay. So just let me know. And I want for us to take notes on one more thing. Yes, Jose. Yeah, no problem.
Okay, I'm done.
Excellent. Okay. So like I said, the reason that we need to know how to do imaginary and complex number operations is because they can come up when we are solving quadratic equations. So let's go back to our example from before. What do we have? I squared minus 2x minus 8. Is that right? Is that what we had before? We had y equals x minus 4, x plus 2.
Yeah, we did have
Yeah, that's what we had. Okay. So we're going to do the same equation because we know that this one has real solutions, and we're going to use this as a reminder on how to use the quadratic formula. Because sometimes you can factor to solve, and that's what you're doing in chapter 5.2, but sometimes there's no obvious way to factor it. And sometimes there's no way to factor it at all. So we need to have a tool that is effective in every instance to solve a quadratic equation, and that tool is the quadratic formula. Yes, Lily?
I was wondering if you're gonna ask what it is.
Yes, Lily is ready with the quadratic formula. So yes, Lily, what is it?
Negative b plus x squared minus the square root of b squared minus 4ac all over 2a.
That's right, all over 2a.
I'm trying not to sing it because a math teacher.
Yeah.
We
Oh,
also
yeah.
have the same song.
Go ahead and sing it.
I don't know the song.
Negative b plus or
I think
minus
about-
the
I think
square
about
root
that
of b
all the time.
squared minus 4ac over
People
2a.
love that song.
That's
at
a
my
different
school.
tune
They
that I know.
sing it all the time.
And I've heard x is equal to negative b plus or minus the square root
No,
b
that's
squared
annoying.
minus 4ac
No.
all over 2a.
Ours is from a
yeah,
YouTube
no.
video.
Oh.
So many different songs.
But like
Yeah.
there was like maybe by like someone in Germany or something.
Yeah,
Yeah.
they're German.
Good. Da.
I
Ja?
I don't know.
Da is Russian. I don't know any German.
I don't know German or Russian.
I know. Yeah, ja is yes, nein is no, and guten Tag. There's a little bonus German to go with your algebra today. Okay, so in this case then, now when we don't have a number explicitly written as a coefficient out in front of one of the terms, what is the number that's implied?
1.
Yeah. Okay, so here, x is equal to, what's negative 2?
Two.
Yeah, so we need to be really careful to mind the signs here. What's negative 2 squared?
4.
4. This is the number one mistake that I see in using the quadratic formula. They put into their calculator
Right.
negative 2 squared.
And that gives you negative.
And that gives you -4 because
Easy
of
for
because of PEMDAS. Your calculator is going to do the square first and then multiply by -1. If you really want -2 squared in your calculator, you have to put parentheses around it so your calculator knows to multiply -2 by -2. Your calculator has no intuition. Yes, Lily.
So, say that I had to find the, so I had to solve for -3 squared. Would that be -9 or 9? From like
It does depend on how it's written, but is -3 your B?
No, it's X.
Oh, you're plugging it in. So then that would have to do it in your calculator. Because the way to think about it, remember, squaring is multiplying by itself. And so if you're plugging in -3 for X and then squaring it, you have to multiply -3 by -3, which will be +9.
So what if it's -X and I'm plugging in 3?
So if it's -X squared and you're plugging in 3, then it is this situation. You're squaring the 3 and then effectively multiplying by -1. Yes. So that's a really important clarification. All right, so but here, yes, -2 squared is 4, -4 times 1 times -8. Again, we've got to make sure that we keep the signs with the coefficients and the constants. Oh, look at that. Oh, we returned to your favorite square. So, Merlin, what's -4 times 1 times -8?
36? No.
Well, because first, for PEMDAS, we've got to do the multiplication
Right.
first. So -4 times 1 times -8.
32.
And what's 4 plus 32?
36.
Aha! Very good. So we're back to 36. And so we've got x equals 2 plus or minus 6 all over 2. And so 2 plus 6 is 8. So we've got 8 over 2, 4, and 2 minus 6, -4 over 2. So we've got 4 or -2. Huzzah! And these were exactly the intercepts that we found when we factored. So we can see that the quadratic formula gets us to the same destination as factoring if there are real solutions. All right. So based on what we just talked about then for imaginary numbers though, Taylor, when might I end up with imaginary numbers or complex numbers when using the quadratic formula? Yeah. Yeah, or if 4 times a times c is more than b squared, we're going to be subtracting a bigger number from a smaller number, and now we're trying to take the square root of a negative number. So let's try this again. Let's say that our equation was y equals x squared minus 2x plus 8. So this is going to start out really similar. It's going to be 2 plus or minus the square root of 4 minus 4 times 1 times positive 8 all over 2. Now we've got 2 plus or minus the square root of 4 minus 32 all over 2. I've got 2 plus or minus the square root of negative 28 over 2. This parabola is not going to cross the x-axis. We're trying to take the square root of a negative number. This is going to only have imaginary roots. All right, now does negative 28 have any factors that are perfect squares? What are the factors of 28? In other words, what numbers multiply together to give us 28? 7 and 4. Is either of those a perfect square?
4 is.
4 is. So, we've got x equals 2 plus or minus the square root of 4 times the square root of 7 times the square root of negative 1. So we can separate out all of the components. This is all over 2. So we've got x equals 2 plus or minus, what is the square root of 4? Yep. 2 times the square root of 7 times I all over 2. And then we can look and see, is there a common factor that all of these components share? In other words, can we divide each of these pieces of the numerator successfully by the number 2? Yes, we can. And so we end up with x is equal to 1 plus or minus the square root of 7i. So this is where this parabola imaginarily crosses the x-axis. These are the complex solutions to the parabola. Okay, you've just covered a ton of ground because people are in different places with where they're working on the material. Go ahead and take it in order. If you have questions, raise your hand. I'm totally available to answer questions. If later today or tomorrow morning you want to watch part of this video again, it will be on Google Classroom so that hopefully everybody has the information that they need to make progress on Chapter 5. Does anybody have any questions about Chapter 5 right now? Okay. So in that case,